Good day. Right, so on a video I made earlier, I talked about weather compensation ratios, and I promised to make a little video to explain those. Now, this was something that was told to me by a commercial controls engineer. I was installing a Eastman 100 for him in his home and talking about the weather compensation curves. And I didn't know this particular bit of information, and he set about educating me on weather compensation ratios. So now it's my turn to pass this little gem of information on to you. So let's return around, and what I've got here is a sketch resembling something like the weather compensation curves that are in the Eastman instructions with their boilers. And the ratio is a very simple concept. These are the same values as you'll see on the Eastman, except for the Eastman curves are actually curved, and on here they're straight. Apparently the original compensation curves were all straight line, and I guess the Eastman have worked out something doesn't quite work when they're a straight line and put a slight curve on them. But you'll find that if you use this ratio theory, you'll be within a couple of degrees of the actual flow temperature on a Eastman for sure, and I would think on most systems. So 2020, so basically we have a flow temperature of 20 and we have a room temperature of 20, so no energy being added to the system. Now the ratio basically refers to the rise in flow temperature in ratio to the fall in outside temperature. So if we have a curve of 1 and we drop 10 degrees, we would add 10 to our 20. So our room temperature is 20, add the 10 that is fallen down, and we should find the flow temperature of 30 corresponding to our curve with the ratio of 1. Now if that ratio had been 2, we would have added 2 degrees for every one it dropped, which would be 20 degrees plus the original 20. We would look up here and find a flow temperature of 40 on our 2 line. And there again, if we were doing underfloor heating, we'd have a curve of 0.5, and that would mean that, so we dropped 10, so we'd expect to see 5 degrees plus our 20, so a flow temperature of 25 on our underfloor when it is 10 degrees outside. Now at 0, we would expect a flow temperature of 30 for an underfloor heating system. And this is where you hear me talking about low temperature underfloor heating. Most underfloor heating systems are set to run around 50. The water's supplied up about 70, gets blended down to 50, and they're operating here. Now, if you look along the 50 degree line, it's minus 20. If you had a curve of 1, which actually I do see a lot on underfloor heating, you'd be looking at a suitable temperature to heat to minus 20. Completely ridiculous and a complete waste of energy. So don't be doing it, boys. Design your systems for low temperature. So a top end of underfloor heating should be a ratio of 1, and we would expect at 0 to be running around 40 degrees. And the government guidelines for heat pumps now is to design for 35. So 35 at minus 2 would be what? Somewhere around 0.8 maybe. We could work that out, couldn't we? 35. So that's 15 degrees for a drop of 22. Yes, it's going to be about 0.8. Can't do the maths in my head. So the government are asking us to design on a weather comp ratio of 0.8. Most underfloor heating systems are between 0.8 and 1. And occasionally we get lucky and we get something down here, but we should be designing down here. People talk about insulation on systems with heat pumps. Now this is where it matters on underfloor heating, because we're trying to get down the number of watts per square meter required to heat a room, and we've got very limited capacity on an underfloor. We can only go to a surface temperature of 29, and that gives us a certain number of watts per square meter output from the floor. And so if we can't make it, the temptation is to turn up the temperatures. Oh, excuse me. So anyway, I think the basic principles are there for you. I think you could follow through the logic. So that's weather compensation ratios. And if you're doing a Wiesmann, you should be able to use that theory quite nicely to decide what your ratio is. Just a quick word on that. So if you're designing for 50-30 on a gas boiler, so you design for a 50-degree flow temperature, you'd be looking up here, down here, and you would probably come to a curve of 1.4, which coincidentally is the curve we set on nearly every Wiesmann we install, which tells us that nearly every radiator installed in the London area is already running a 50-30 design for a gas boiler, which means a mean water temperature of 40. So if you're heat pumping, 42.5 would be your flow temperature. So that's a curve of 1. So basically we're down into heat pump territory, underfloor heating territory with the radiators. And this might explain why we're getting people claiming that they're designing radiators and underfloor to run at the same temperature, and they're probably getting it on this ratio down here. Now I would argue that that's very good for radiators, very normal for radiators, but it's not that great for underfloor heating. So if I was going to install a system in a new build and someone told me to design the underfloor to the same temperature as radiators, I would ask the question, why did they want me to make such poor design criteria for my underfloor heating? And this is when I would be using mixers. I'd be having my underfloor down here somewhere and my radiators down here somewhere, and using variable temperature mixers on there and keeping those floors cooler. Now that would also give us a better comfort level, I believe, in the property if we did that. So okay, well I hope that helps. Thank you.